Hello, good evening, everyone, or have a nice day to everybody. So, for today, we will be going to talk all about pertaining to the graph data structures. So, if you are familiar with the graph data structures, so I think that um, you, I think that this is somewhat familiar to everybody since of course when we say graph it's a core of data structures which somewhat similar to the trees algorithm that we also discussed last time. So now let's try to check what is graph. Then let's define graph. So when we say graph, it is a data structures, a nonlinear data structures, which is a collection of the nodes or the vertices that have data and are connected to other nodes. So that's what means with a graph. So that means to say in our graph data structures, it is a collection of particular nodes and that is connected still the same. Vertex or a node is connected via the connecting links or the edges. Now we each edge connects two nodes together or possibly the same node to itself and may contain an edge attribute. So that is how graph work. And our method used to manipulate and analyze graph, solving various problems like finding the shortest path and more. So in a data structures, in a graph data structures, when we say routing and navigation, um, I mean shortest path, that is somewhat in application of the routing and navigation. Since graph can be applied in a routing and navigation, social networking analysis, recommendation system, and computer networks, and more. So talking to that one, routing and navigation that pertains to you are using those in GPS system using the shortest path algorithm. There will be a Dijkstra's algorithm. It could be like that, Prim's algorithm, or um, we will be going to check that later on, especially with the Kruskal's algorithm and so on. So in our current society, or in the real world right now, networking is all on working analysis in terms of you are using the graph algorithm since that is a fundamental of in design managing the networks, computer networks such as like that, um, to optimize the flow. It could be like that, or the connectivity and communication protocols of that certain network. And pathfinding navigation is what I mentioned earlier, that you are using the GPS and mapping application in order for you to determine the most efficient routes, such as Dijkstra's algorithm and so on. Now, here then, let's try to define the representations of what is the representations of graph data structures are. So first of that one will be what is all about there. We have here in our graph, we do have the vertex, which is defined as the fundamental unit by which graph are formed and can be labeled or unlabeled. So when we say vertex, this is your node. This is the vertices that contains the data itself. So it is somewhat labeled here as A or B, something like that, and that is the element is being stored in that particular vertex. Now, next will be the, we also do have here the edge. When we say edge, a connection between two vertices and can be labeled or unlabeled as well. So since in our data structure, graph data structures, this is our edge. And that edge do have a labeled if there will be a weight, something like that, as a representation or the amount of values that contains in that certain edge goes to another relationship of nodes, something like that. So that actually how does it work, the graph. Now we also do have the next one, which will be the degree. When we say degree, that is the same similar, similar to the tree algorithm that we have um, in our tree. We have the degree of a tree, which means how many child does that vertex or does that node contain. So here then in our graph representation, this is also talking to the number of edges which is incident to that vertex or the number of edges which is connected to that particular vertex. So that is the degree. So this is still, for example, in your A, how many will be the relationship or what will be those connecting links direction that is pointing to what vertex. So here our A is adjacent to B and D and C. So you will just count that one. How many are they? That is the siblings of A. If we will begin to talk all about with the trees, diba? So that is defined as three right now, and this will be here let's try to check that later on. So this is actually a degree of undirected graph. Since our graph right now here in the presentation, that is undirected, which means that there were no direction um, specific in that one. So when we say in a undirected graph, I mean, that is simply the count of edges, which is incident to that. So what will be? If you will count that one, what will be the incident of A? So that will be the CBD and CBD, diba? That is three. So that is how you will identify the degree of a graph pertains to undirected graph. So you will just count how many incidents into that particular vertex bar. Now, we also do have here the degree of a tree, which is in a directed graph. So in our directed graph, we do have two different representation. So the first representation in that one will be the in degree directed, in degree of a tree. So that is talking to the number of edges which is coming into a vertex. So say, for example, when say coming into, that is, for example, you are at A right now. How many edges which connect to A that points directly to A? That what means for in degree. In vernacular terms, pila ka bilog nga arrows ang gapakadto sa iya, gapakadto sa imo, something like that. Now, in our A here, we only have one. How about in your D? How many in degree? So that will be B points to D and C point to D. So that means to say we have here a 2 degrees of letter D. Let's try to see. Baha, correct. And for E, let's try to check why is it considered as number 3. So that since E is incident to B as well as D, and also there will be a loop here that returns to itself. So that is actually count right now as a additional degree. Okay, we also do have another representation for the degree of a directed graph, which will be the out degree. So when we say out degree, the number of edges, which is actually going out from a vertex. So when we say going out, that is talking to what will be or how many arrows going out to that particular tree, to that particular edge, I mean. So in our A, how many those arrows which connects or to another vertex or going out from A? So A is connecting to B and connecting to C. So that means to say right now, the out degree relationship of A will be the B and C only, since D path that goes to A is not considered as an out degree, since that is pointing to letter A. So now, if we will identify the out degree of A, that is equals to number 2. Diba? Correct? So here then in your E, that is only one, since only one will connect to itself. And that is how the graph worked here in the degree of a 3-4 directed graph. Now let's move on to the next representation, which is also talking to the isolated vertex. So do you all actually have a like idea of isolated graph? So when we say isolated graph, that is actually talking to a vertex in a graph that has no edges that connected to that one. So in that here, if I will ask you, is there any isolated graph, which is in that graph right now? So there is nothing. So there are no isolated vertices in that one. So how can we consider, or how can we identify that there were a isolated vertex? So say for example, there will be an F node here, which is not connected to that A, B, C, nor to D and E. So of course, that signifies that there's no relationship to each of those particular node. It must be a single, excuse me, single node alone. So that actually represent that F right now is considered as our isolated vertex. Let's move on to the path. So in our tree algorithm or data structures, we also identify path that it goes to what particular node. So from the root node, what will be the path down to the right subtree or whatever in our tree. And here then we also do have a path. This is a sequence of vertices where each adjacent pair is connected by an edge and as a sequence of edges that allows you to go in anywhere of the tree, graph. So say for example, our initial state here, suppose that we are starting from the letter A, node A, and my goal is the letter E, and I want to achieve or I want to go into the letter E. So that means to say, what are those paths that I can take when I will go in that certain graph. So that means to say, halin sa A, ang akon nga path nga agyan is coming from A goes to B, pwede man B goes to E. So that will be the only path right there. Excuse me for a while. So actually, regarding with that one, there will be a lot of path that you can also identify, not only with that certain ABE alone. So there will be A goes to B, goes to D, and goes to E, something like that. It can be considered as a path as well. So in that particular graph, other than that, there is also AC and goes to D and goes to E. That will be considered right now as also a path of that certain graph. Now, let's actually move on to so as what I mentioned earlier, that will be the path that we can follow goes to the E from our initial state. Now let's actually move on to the next representation, which is the cycle. So when we say a cycle, that is a path that starts and ends at the same vertex without traversing any edge more than once. So when we say a cycle, we are starting from our initial state and we also end in that initial state. So for example, you are starting to visit or you are starting to traverse from letter A So it must be, you will also go from A, then goes to A itself. So how can you do that? So there will be a path AB, BD, and DA. So that's how cycle work is. So now in that particular graph, if you will also check if, for example, if you are in the node E right now, is there any path that for the letter E? So in that E, considered already the letter E, since there is a loop right there, that loop to itself. So that is considered as a path already then. So here are the some suggested path, which you can also check. ABDA, there is ACDA. Let's try to check. That's correct. And BDAB, BDAB, that's correct. CDAC, CDAC, good. And DACD, DACD, very good. That is actually the path that we can take there, and also the E as what I mentioned. Now, let's actually move on to the next representation, which is the subgraph. So in our tree algorithm data structure, we also identify all about the subgraph, subtree that will be those structure within your tree that forms another tree that is considered as a subtree, di ba? Amo man na siya sa aton nga tree. But here in the graph, a subgraph is a form from a subset of the vertices and edges of a larger graph, which is a subset of another graph consists of a selection of its vertices and edges. So of course, by the way, just to also remind you everybody that in our graph, even a single vertex that also can be considered or can be treated as a subgraph. So B alone is a subgraph already. A to B can be a subgraph. ACD, a subgraph. ACDE, that is a subgraph as long as they are they're considered as another graph. So because here in our graph data structures, we do have a lot, actually a lot of types of graph that I will also, what we call this one, that I will also discuss to you in the next video, so that you will also be aware of what are those types of graph. Now, so here, ABD is what I mentioned and more. Not only that certain vertex form as a subgraph, there will be a lot actually, as what I mentioned. So next here, we also do have the adjacent vertex. When we say adjacent, a two vertex are said to be adjacent if there is an edge which is connecting them. So say, for example, A and B. Is there any connection for that one? So that we can also consider that they are adjacent. So A and B, there is a path or there is a connecting link. So that means to say A and B are said to be the adjacent vertices. So in your A, if you will also see what will be those adjacent vertices. So that will be the B, that would be the D, that will also be the C. So that's how you will identify the adjacency of that particular vertex. Now we also do have a adjacency of a edges. So the adjacent of edges are edges that share a common vertex. So common vertex of, say, for example, this path or this edge, what will be the vertex that connects to this one? So say, for example, A and D. So we do have connecting edge, the same connecting edge. So why is there is an adjacent edge? Because this will be also useful. For example, like a weighted graph. For example, we do have a weight, there is a representation like here, identification that this is the value of that certain graph. So say, for example, I want you to identify the what will be the adjacent edges for the number 10 edge. So that will be, you will check what will be the adjacency for that. That is A to D, diba? So that's how you will do that here. So anyway, that's the end of our first video. That is all about the graph representation only. So in the next video, I will also discuss the types of graph and so on, the operations and everything. Okay, so thank you so much. And if you do have any question, just comment below, and I will also get back to you that one. Okay, thank you.